Hello, I welcome you all to this another interesting screencast. We are going to be solving this engineering mechanics problem. And the problem reads the annular ring bearing is subjected to a thrust of 800 pounds if the coefficient of static friction mu s is equal to 0.35. Determine the torque M that must be applied to overcome the friction. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we've got here a ring bearing, okay, subjected to a thrust force of 800 pounds as shown. And not only is the thrust force, not only is the ring bearing subjected to a thrust force, but there is also some torque or moment, okay. And we are being asked to determine this magnitude of moment or torque that is supposed to overcome the friction. Right. So let's draw our coordinate system that we are going to use. So this is our coordinate system. This is our x and this is our y, positive, and z is coming out of the screen. So we have this bearing, and we are going to experience friction at the point where the bearing is in contact with the supports, where I'm drawing these red lines, okay. We are going to experience friction force. All right. And we are now being asked to determine the moment that is going to overcome this friction force, okay. All right. So let's draw the free body diagram. So I've removed this structure, okay. I just want to concentrate on the bearing. So at this point here, I expect very, very small normal forces, dNs, okay. Okay, and if I was to integrate these dNs over the whole area, okay, I'm going to find the total N equivalent force, and there we're going to have an N, we'll have an N, we're going to have an N like that. Right. Okay, what else? So if I was to cut a section, I cut a section so that I look at one of these rings. I cut a section like so. I'm going to see something like this. Okay, just want us to look at what is happening. So I will have something like this, the outer diameter and the inner diameter. All right, like so. So I'm going to have again over this same place where I have the very, very small dn. I also have very small dA, the area, and on this area we are going to be having or have a very small friction we are calling dF. Okay, this is the one that we want to overcome, and this dF is acting at a centroidal distance r from the center of this bearing. Okay, so we have this distance here. This distance here is r. Let me use another color. I use maybe green. We have this distance here. So this distance here is centroidal distance r. Okay, so we have small area, small df, which is our friction, which we need to integrate so that at the end of the day, we have the whole friction force. So now this is how everything looks. Okay, so now let me write the equations of equilibrium. We're going to have two. Summation of forces in the x, considering my coordinate system, which is here. So summation of forces in the x direction equal to 0. So I have minus p, which is 800. Okay, and then plus 3n equal to 0. So on each particular ring, we are going to experience friction. Okay, but the n itself is equal to 1/3 of p. Okay, which is equal to 800 divided by 3. Right. And then the other equation of equilibrium, we'll call it summation of moments about the x-axis. Okay, using the right hand thumb rule, this moment that we have right now is a negative. It's a negative, so minus m. Then this infinitesimal, this df, is also going to cause some moment about the center of this particular bearing, about O. Alright, so if we are to integrate all this, then we are going to have the following expression. So minus m plus integral of r df, okay, equal to 0, where df is equal to mu s dn. Okay, so you don't have to really worry so much about all this, because we are not deriving anything. These things have already been derived. I just wanted to speak about the preamble of the derivation that was already made. So when you integrate everything else, you find that, because you realize that r is going to be changing, right, as well as the angle, okay, because this df is everywhere along this area here. Okay, see in this area. Okay, so when you integrate that, then you are going to finally find the following expression, which is m is equal to 2/3 of the friction force times the thrust force P. And if you want to check how this integration was done, you can just get back to your book and check the work. We are not doing any derivations. Then times R2 cubed minus R1 cubed divided by R2 squared minus R1 squared. So this is the equation that we're going to use. Alright, so now what is our R2? Our R2 is our outer diameter. R2 is equal to from the center of our structure bearing, the inner ring is is 2 inches, and then R1 is 1 inch. Mind you, we are just interested in this area here. Okay, this area. Okay, from there to there. This area from there to there. This is the area we are interested in. Okay. Okay. This area where we have the ring itself, the bearing in contact with this member here. We're just interested in this part here where I'm drawing the red. Okay. This is the part that we're interested in, just this part. Alright. So R1 is therefore equal to 1 inch. Okay. And the mu s is already given in our problem. It is 0.35. And then P is also given. It is 800 pounds. If we had different values of P at every ring, okay, then we could have considered that, right? Because at the end of the day, what we need is the moment that is going to overcome the friction being created by what? The friction force. So that friction force is causing a moment, so we want to counter that moment, all right? So we want to know how much moment we want to apply to overcome that friction. So if we had different values of P, imagine we have this P, then we have a P2 here, we have another P3. We could have considered all those, okay, because this will have different effects, right? This time around, we only have one P on the furthest end. And we said the equivalent N at every ring is what? Is P divided by 3. Okay. So there we go. Therefore, our M is going to be equal to 2/3 of 0.35 times um, times 2 cubed minus 1 cubed divided by 2 squared minus 1 squared. And if you work out this problem, you find that you're going to find a 435.5 rounding off to 6, okay, pounds inch. Okay, so our moment is equal to 435.56 pounds inch. So this is about it. And I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye, and see you in my next screencast.